Let's review really quick. If I were to start off my sentence with the derivative is, how could you finish that? The derivative is slope of the tangent line. I heard that. Instantaneous rate of change, or slope at a point. Like, so if you think about a curve, the slope at any particular point, slope of the tangent line, or instantaneous rate of change. That is what the derivative is. So in number 3, let's talk about it. There's some finer points here I think are definitely worth bringing out. Notice the very first word of the sentence. What is it? Estimate. Estimate. So this is something I feel like can be kind of a struggle because simply we're not used to doing it. I mean, how many times, think about it for a second, how many times in a pre-calc class, Algebra 2 or whatever, did the question say estimate or approximate? Not very often, right? Isn't it usually find the answer, find the solution, et cetera, et cetera? And so estimate is usually not something that's common. And so because of that, I think it's worth talking about what tools we have in order to estimate, what we could use to estimate. So let's try to break this down right here. So it says estimate f prime of 3. What does f prime of 3 mean? What does f prime mean? The derivative, right? So you could say a slope of the tangent line, the derivative, f prime means that. What do you think about the of 3 part? Where we're finding it, right? So we could say that f prime of 3 is the value of the derivative at 3. You could say the slope of the tangent line at 3. You could say the instantaneous rate of change at 3. So estimate the slope of the tangent line at 3. And this is where it goes a little weird. If f is represented by the table. So what's going on here is we have no idea what f of x is. We don't know if it's a parabola, a cubic, a sine, a cosine, a tangent. We really have no idea what it is, but we do know that someone has gone before us and done some inputs and outputs for this function, and that's represented by the table. So when x is 1, y is negative 6. When x is 5, y is 3, so on and so forth. We are supposed to figure out what an approximation for f prime of 3 would be simply using the data in the table. So it's kind of a big leap just to jump right there, but I'm wondering if you have some thoughts, like what could we use to get there? What do you think, Peyton?
So you could take the slope between x equals 1 and x equals 5,
okay.
And because f prime is what the slope is and 3 is in between 1 and 5, you could sort of make the assumption that it's going to be close, so the estimation will be sort of done.
I have no problem with anything you said. I think it's great, except the end. I think I would tweak a little bit. You said, what he basically said, tell me if I said this right. He said we could use the slope between 1 and 5, right? Because 3 is right in the middle of 1 and 5, isn't it? So that seems reasonable. And then at the end you said, because we could maybe assume that the slope between 1 and 5 would be sort of close to the slope at 3. We don't know that, do we? We really don't. So what we could say though is that the slope between 1 and 5 is probably the best estimate we have. We have no idea if it's close or not. It might be, it might not be close at all, but it's the best that we have. It's the best that we have. That makes sense? Based on the situation, based on the data we have, we kind of have to go with that. So that's really well said. That's a great strategy. So I'm going to write it like this. I'm going to say f prime of 3 is approximated by, how do we find the slope between 1 and 5? What would that look like? Say again? The slope formula, yeah. So if we're going to use that slope formula like delta y over delta x, Johnny, what would the top of the fraction look like?
9, or 3 plus 6.
Yeah, 3 minus negative x. It'll end up, of course, being 9. And the denominator then would have to be what? 5 minus 1. Good. So this is something important for us to think about here. There are going to be times when you will have to really answer a question just like this. Honestly, you'll have to answer a question just like this. And one of the important things that I'm going to be looking for is that you used a difference quotient. And that's what that is up there, right? 3 minus negative 6 over 5 minus 1. So I would like to show you some things that would be totally correct, yet would not give evidence of a difference quotient. For instance, you're all very good at arithmetic, so you might have just written this. Like if you just wrote 9 over 4, that's the correct answer, isn't it? But did you, by just only writing this, did you really show that you used a difference quotient to get there? No, you did not. You just showed a quotient. And so I think it's really important. I only say this because Johnny was obviously very quick with the arithmetic, which is great, but make sure you show that step where you say, hey, I did a difference quotient. This is what I'm using. And of course, the answer is 9/4. The answer is correct. So if that were a 2-point question, that'd give you both points. If it were a 2-point question and all you wrote was the thing I'm circling in yellow, you would get 1 out of 2. So show your process, and you'll always be in good shape. Make sense? That was really well done. Peyton, thank you for that strategy. Great job. Any questions from anybody? Okay, so the little saying off to the right there I think is worth finishing here. It rhymes, so hopefully it's easy to remember. So this asked us to find f prime of 3, but we didn't know what f of x was, so it was really impossible for us to find f prime of 3, right? And so the saying goes, if you can't differentiate, like we couldn't here, if you can't differentiate, that's fine. Just use the slope of what? What did we actually use the slope of? Secant line, right? So just use the slope of the secant line. Believe it or not, you will use that phrase a ton. You'll use that phrase a lot, or at least that process a lot, as we go through this. So if you can't differentiate, that's fine. Just use the slope of the secant line to approximate that derivative. Happy? Okay, cool. So I hope that you guys have been paying close attention and you did well. Peyton obviously gave us a good strategy. I hope that made sense to you. If you have spaced out a little bit in the last 5 or 6 minutes, now's the time to come back, okay? Come back with a vengeance, full mental focus. What I'm going to show you here is something that is an extremely common question. Doesn't mean that it's easy, doesn't mean that it's difficult, it just means it's extremely common. So this would be something that you want to make sure that you have solid, okay? You want to make sure you know how to do this. So let's read this. It says, what is the value of k plus c if f of x equals that piecewise function is everywhere differentiable? So essentially what we have here is we've got a parabola, that's the top piece, and we've got a cubic, that's the bottom piece, and we want to figure out what the k and the c would have to be so that these two functions are continuous, right? There's no jumps or removable discontinuities or anything like that. And not only that, but there's no sharp points either. So it's a smooth, continuous curve. We want to figure out what the k and the c are. To help us get started, I want to ask you guys a question. Differentiable. Differentiability implies what? Continuity. That's right. So I'll put out here, just in parentheses, that also means that the function would be continuous. If it's differentiable, it has to be continuous as well. So here's what we're going to do. We are going to start by writing a statement that will guarantee us continuity. If I'm going to write some statement to get me started with continuity, what do I have to use? What's got to be there? Got to have limits, right? Remember that statement, limit from the left equals limit from the right equals the value of the function. So we're going to reuse that. So I'm going to write it like this. Limit as x approaches 3 from the left. What would be the left piece in this piecewise?
The bottom.
Yeah, the cubic, yep. So of x cubed plus cx has to equal the limit as x approaches 3 from the right. Of course, from the right would just be the other piece, the parabola there. So 2k x squared minus x, and that has to equal f of 3. Bless you, which piece actually contains f of 3? The bottom piece. So I'm just going to go ahead and plug in the 3. So 3 cubed is 27, so it'd be 27 plus 3c. So that's that limit statement regarding continuity. Does that make sense? Any questions? We've done that a lot, but it's good to remember. Okay, now let's progress a little bit. What is potentially the easiest way to evaluate a limit like this? Just plug it in, and you're going to find that that works here. So if I plug in a 3 using direct substitution, I'm going to get 27 plus 3c equals 18k minus 3. And then, of course, the 27 plus 3c you can see now is kind of redundant, right? So I don't need to write that again. I'll just write it once. Well, awesome. There's a really wonderful equation. You guys feel like you could solve that? Why not? Some of you are saying nope. Why can't we solve that equation? two variables. So what do we need in order to find the k and the c? Another equation, right? So it's a two variable system. So if I've got two variables, I have to have two equations that are related to each other. So what did this, like this whole process that we just did, what did that work with? What did that guarantee? Continuity. So if that equation is true, then this piecewise is continuous. What have we not dealt with yet? Differentiability. So in order to deal with differentiability, what I'm going to do is I am going to find f prime. And this is where I'm going to rely on the fact that you've seen the power rule a little bit in your past. And if what we're about to do is a little shaky, don't worry about it. We'll get it down. If you watch the video, you probably recognize this. But what I'm going to do is I'm going to write f prime. And f prime is equal to, we got to find derivatives. So let's just use the power rule, for goodness sake. Let's not use the definition of the derivative. What do you guys think the derivative of 2kx squared is? It's 4kx. The k is a constant. So it'd be 4kx. And then what is the derivative of minus x? Minus 1. So f prime equals that when x is bigger than 3. And then how about the other piece, the derivative of x cubed? 3x squared. You guys got it. Nice work. And in this case, plus cx. What's the derivative of plus cx? Plus c, because the c is a constant. So the derivative of cx would have to be plus c. That's for x less than or equal to 3. Okay, so essentially for a function to be differentiable, we want the derivative from the left and the derivative from the right to be the same. So one of the ways you could work with this one would be to say this. The limit as x approaches 3 from the left of f prime has to equal the limit as x approaches 3 from the right of f prime. That make sense? We want the derivative from the left and the derivative from the right to be the same. You follow me? If the derivative from the left and the derivative from the right are not the same, don't we get like a sharp point idea? But if we take this part and we change its angle to be that, don't we get something that is differentiable? So I want to basically make sure that this angle is the appropriate angle so that we don't get the sharp point. Okay, fair enough. So let's go ahead and evaluate these two limits. So we've got f prime up there above. So which one is from the left? The bottom one, yeah. So 3x squared plus c. So let's evaluate that limit as x goes to 3 from the left. So if we do that, what do we get? 27 plus c. Good. Equals, how about the other side? 12k minus 1. Makes sense? Just plug in the 3 in for the x. Okay, so 12k minus 1. All right, this is great news because I've got an equation right there. I've got an equation right there. They both have k's and c's. Why is this such good news? We can solve it using a system. Now, this is not a matrix question, right? You've got to be able to do this by elimination or substitution. This is actually right off of an AP test from about 10 years ago. And it was on the no calculator section. So you have to be able to do elimination or substitution and do it well. So what do you see? What do you think would be easier, elimination or substitution? I personally see substitution. What I think I would do is I would take this bottom equation and solve for c. So c equals 12k minus 28. And then I would just take the 12k minus 28 and substitute it in for c right there. That make sense? Okay, so can I let you guys finish that and see what you come up with? Let's just make sure we can do the whole substitution thing. I'll give you just a minute, we'll check your answer. Okay, so if you do the substitution, that next step in green on the right there, that's what it should look like. I mean, just did the substitution, that's it. If I distribute the 3, it's 27 plus 36k minus, 84 is equal to 18k minus 3. If I start adding my like terms up, I'm going to get, let's see here, 18k over there. That's negative 57, so plus 57 equals 54. So did you guys get k is equal to 3? Is that good? Okay, so if k equals 3, then c is equal to 12 times 3, which is 36, minus 28 is 8. Yeah? Okay, cool. So k plus c is what we were originally asked for. 3 plus 8, of course, is 11. So that'd be our final answer. I don't know about the whole k plus c. There's no real significance to that. Like I said, it was just off some old AP test, so I just kept it the same. The point, though, is can you find the k and the c? Kind of a big process. I get it. Do you have any questions other than I need to practice it, that kind of thing? Any technical stuff I can help you with? Why something is there, why something isn't there? What happened to such and such? Yeah, Jake.
The other thing is, like, when we do the second limit with the derivatives, does that also have to equal f prime of x? Because, like, in the first one, when you're...
No, it really doesn't. It's just simply the behavior from the left and the behavior from the right. So if a function is not continuous, it's also not differentiable.
Yeah.
So by guaranteeing the continuity, we've said, okay, if this thing really is continuous, that's really all we have to do is just the two-sided limit with the derivative. Great question. Matt?
So if you could prove that the derivative, the equation for the derivative is continuous, then
Yep.
you don't have to prove that the...
Well, yes, but in this situation, if you did that, you'd only have one equation,
Okay.
and you got to have two. So your supposition is correct, though. Yeah, definitely. It just wouldn't work for this particular question.
Right.
Yeah. All right, anybody else? Okay, fantastic. Well, let's see what we can do with 2.2, which is right here. So here's where the video starts. And really, I think, correct me if I'm wrong, but I believe in all of the pre-calc classes, everybody saw the power rule, right? Whether you were in the DC version or the non-DC version, I think you all saw the power rule, right? So if you didn't watch the video, maybe there was that confusion we talked about, go back and check it out. There's the constant multiple rule, ideas about sums and differences, and then that little check for understanding you can see right there. So let's take a look then at a couple of examples, starting with number 8. It's a good one. We'll take our time here and talk about what's actually happening and hopefully come up with a good answer. So this says, find the slope of the tangent line in the equation of the tangent line. Or question number 8 says, for that cubic, find the equation of the tangent line at x equals 1. What I would like to do before we do that, I would like to try to illustrate what it is that we're talking about. And so I am going to try to draw this in. So if I were to find x equals 1 on this cubic over here on the right, I would say that x equals 1 would show up right about there. Does that look about right, where I've drawn in that point? Okay, so we would call that, because it's where the tangent line intersects the curve, we would call that a special name, the point of tangency. And so at that point of tangency, two things are true. Or what they are? Well, yeah, it is continuity, yeah, but in regard to the relationship of the tangent line that we're about to draw and the curve. Two things are true. I thought I heard, not perpendicular, something about parallel-ish, kind of same slope. There it is. So if I were to draw in this tangent line, and I'm going to totally cheat and do this. Something like that. That's my line, nice straight line. Actually, let me do a little better than that. Let's go with that. Okay, so at that point of tangency, the two things that are true are this. The slope of the curve, so I'll just put slope C equals the slope of the line. So the slope C equals, boy, you can't see that, can you? Let me retry that. Well, slope of the curve equals the slope of the line. Better? Slope of the curve, slope of the line are the same at the point of tangency. Can you see that once you move off the point of tangency, that's no longer true, is it? Once you move to the left or the right, well, now the curve of the, or the slope of the curve and the slope of the line are now different. Yeah? Okay, the other thing that's true is that the xy for the curve is equal to the xy for the line. They have to be the same as well. So at that point of tangency, those two things are true. The minute you move off the point of tangency, those two things are not true. Make sense? Okay, so here's how we do this. With that in mind, it says find the equation of the tangent line at x equals 1. We're going to try to find the equation of that line. What are the two things that you got to have to find the equation of a line? This is from Algebra 1. Point and a slope. Point and a slope. Of those two things, don't I sort of have half of one of them? I have half the point, right? Let's find the other half the point. So I know that my point of tangency, point of tangency is going to be 1 comma something. How do I find the y to go with that x?
Plug it in.
Just plug it on in, right? So if I take the 1 and I plug it in, I get y, or let's use the right notation here. F of 1 is equal to what? 1 minus 9? Negative 8. So you could say the point of tangency is f of 1 equals negative 8, or you could, the traditional way, 1 comma negative 8. So we got the point of tangency. That's that point right there. And you can see 1 comma negative 8. That looks about where that is. But now we got to find the slope of the tangent line. And when I say slope of the tangent line, what is that? That's the derivative, right? That's going to be f prime of x, or dy dx. So let's find that. So f prime of x, the easiest way to find this is going to be to use the power rule. So let's try that. The derivative of x cubed is 3x squared, and then the derivative of minus 9x is minus 9. So that's going to be the slope of the curve anywhere on the graph, right? We don't care about the slope of the curve anywhere on the graph. What do we care about for this one?
At 1.
At 1. And so I want to find f prime of 1. That would be the slope of the curve at x equals 1. So I got to just plug in a 1. So if you plug in a 1, what do you get?
Negative 6.
Does that agree with the little picture that I tried to draw? Does it look like that line has a slope of negative? It's definitely negative. And it's pretty steep, so negative 6 seems reasonable. So now we've got everything we need. We've got the point of tangency. We've got the slope of the tangent line. All we have to do now is put this together. And here's where I would encourage you to, how would I encourage you to put this together? Do you guys remember point slope form? Just use that. So here's what I would hope you would do. I hope that you would write y minus negative 8 equals negative 6 times x minus 1. Done. You know how we feel like we always have to go to slope-intercept form? Like if we don't do it, we're not done? Yeah, some people feel that way. Like, oh, we're not done yet, are we? We're done. Isn't that the equation of that line?
Yeah.
Plus b.
Seriously like that.
There is no plus b.
There isn't. Oh,
No,
right.
that's point slope right there.
That's why
We could
it's
get to the
plus b.
plus b thing if we wanted. We could get to y equals mx plus b by distributing and adding, I guess it would be subtracting 8
But we don't.
from both sides. But we don't have to do that. No. So any form of a line is okay. In fact, if you look at old College Board material stuff, you'll see they use all kinds of stuff, some of which are like not an official form of any line. They like sort of have, it's like a hybrid between point slope and slope intercept. All these things are equations of that line. I'm not going to get picky about which form you use. And to me, that's the easiest one to use, right? Because it's just like plug, 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 done. There's no arithmetic for us to mess up. It's just, if you can plug it in, you're good. So I would encourage you to use that. Anybody want to go to slope intercept form?
Yeah.
Okay, let's do it. I know some of you are like, but, it's not what I'm used to. Okay, so let's see here. It would be y equals negative 6x plus 6 minus 8, so it would be minus 2, right? Negative 6x minus 2. And, wow, I got to celebrate this. That's actually a pretty good line that I drew there. This is rare. Look at that y-intercept. You see it? It's pretty close to negative 2 there. Woohoo! Feel good about that. And so hopefully that all makes sense between the graph and the process we just did and the equation that we ended up with. Do you have any questions? Fantastic. All right, so let's take a look at B then. B says find the x values where f of x has a horizontal tangent line or tangent lines. So let's think this through. A horizontal line has what kind of slope? 0. And the slope of the tangent line is the derivative. So What B is asking us really to do is
Find the zeros of the derivative.
find the zeros of f prime. Set f prime equal to 0 and solve. Does that seem logical to you? If it doesn't seem logical, you need to say something. Horizontal tangent lines have 0 slope, and so to find horizontal tangent lines, we want to set the derivative, the slope of the tangent line, equal to 0 and solve. So it would look like this. We already found the derivative. We would write 3x squared minus 9 is equal to 0. And then we'd add 9 to divide by 3, so we'd end up with x squared is equal to 3. How do we finish that off? Square root. Yep, square root both sides. But remember, when you square root both sides, yeah, plus minus. So x is equal to plus or minus the square root of 3. So let's see if this makes sense with the graph that we have up there. Horizontal tangent lines would happen at these smooth turnaround points like there and there. What's the square root of 3 roughly?
1.7.
Well, 1.7-ish. Do those look like they're at about 1.7 and negative 1.7? It's pretty darn close. They both look like they're roughly at plus minus 2, which is pretty close to plus or minus 1.7. And this is just a picture right off my calculator, so I'm assuming that it's fairly accurate, hopefully. So there you go. Really important question, right? In fact, I would say pretty much all the examples are important. I'm not going to give you any fluff of like, hey, this is like a really unimportant question. This one's really huge. Finding the equation of tangent lines and then those horizontal tangent line locations, definitely a key thing. I'm reading confidence, but I could be reading you wrong. Am I right? Okay. Okay, awesome. Well, let's keep on going. We're moving along pretty good here. So the next, there's just a couple to go here. Sine and cosine, then rates of change. This is going to work out just fine. Okay, so can I give you these rules here really quick, and then I'll explain at least one of them? Is that okay? So the derivative for sine is cosine, yep. And the derivative of cosine is? Negative sine. So there's a lot of ways to prove these. I personally prefer a graphical method. I don't know if you've seen this, but I will show you this. So here is the y-axis. There is the x-axis. Here is a graph of, okay, you want to do cosine? Oops, here's a graph of cosine. Something like that. So I'll label that as cosine. Here is a graph of sine.
And then it'd be 0.
Like so. So that's, the green one is sine of x. So let's talk about how these relate to each other. Let's focus, so we're doing the derivative of cosine, right? So the derivative of cosine, let's think about the slope of cosine. So I will use a blue color to represent this. What do you think the slope of cosine is right there when x is 0? It looks like a 0 slope, right? It looks like a horizontal tangent line. And coincidentally, what is the value of sine when x equals 0? 0. So the slope of cosine seems to match the value of sine. Make sense? Okay. Then if we look at something like this, doing it this way is a little bit harder to see, but I think it'll be all right. So let's look at this. So you're going to have to guess at this. What does that look like as far as the slope of cosine? If you just had to guess, negative something. Specifically, if you found the derivative and calculated it, you'd find out that the slope of the red graph right there is negative 1. What's the value of the green graph at the same spot? It's 1, right? Isn't it the opposite of that? So the slope here is negative 1, but the value of the green graph is 1. So you see how they're opposites? We couldn't really see that on the first one because the opposite of 0 is just 0. So it doesn't really show what we want to see. But since the slope of cosine is negative 1 and the value of sine is 1, we see that they're opposites. Do we see the 0 pattern again here and here? The slope of the red graph is 0. The value of the green graph is 0. And then lastly, right here, what would you guess the slope of the red graph is? 1, positive 1, right? But then the value of the green graph is negative 1. So again, we're seeing that opposites pattern, and that's why, at least intuitively here, we can say, hey, looks maybe like the derivative of cosine would be the opposite of sine. It's a little easier to see if we do the other one, but this certainly works out just as good. Okay, any questions? All right, so let's take a look at number 9. I'll have you mess around with number 10 a little bit too here in just a second. But with number 9, it says g of t is equal to pi times cosine of t, and it says differentiate. So we could write this as g prime of t. What would you say this should be? Pi, remember, is a constant. T. I would write it in a slightly different order. I'd write negative pi sine of t, but of course what you said, Ben, is correct. We're just used to having the positive negative thing on the front, but it makes no difference really. So negative pi sine of t is correct. Okay, and you guys know on your WebAssign, WebAssign is like insanely picky. Like if the independent variable is t and you put x, what's it going to say? Wrong. Until you go back and put a t instead of an x. So just so you know, WebAssign has no flexibility whatsoever, and that's actually a good thing. It's a frustrating thing, but it's a good thing. All right, and then the other one, number 10, I'm hoping that the second term is not too big of a deal based on what we just talked about, but the first term, kind of a big deal. What do you think we should do with that first term before we consider any differentiation at all?
Flip it to the top.
Yeah, we've got to do some algebra, right? I'm thinking before we flip anything to the top, I think we will eventually do that. I would like to deal with the parentheses 2x cubed. So if we did simplify that, what is parentheses 2x cubed? That's right, so it'd be 5 over 8x cubed, and then still plus 2 sine of x. And this is where I think Matt's idea of flipping is the right idea. So if I was going to flip, he didn't really say what was going to get flipped. Any suggestions on what should flip and what it would look like if we did that? The x cubed needs to be flipped. What about the 8? Does the 8 need to go up too? I don't think so. I think we leave the 8 right where it is. So I think I would write y equals 5/8 times x to the negative third plus 2 sine x. That's an 8 down there. Here's something that's kind of deceiving. How much calculus have we done? How much differentiating have we done? None. Have we just done some algebra? It'd be really easy to do what we just did and be like, sweet, did it. No, you didn't. You didn't finish it. You did some really good algebra, but you have not finished it. Let's find our derivative using power rule, as well as the second term would just be your rule for sine. So, Nick, what do you think? What's the derivative of 5/8 x to the negative 3?
Negative 15 eighths over x to the fourth.
Can I just write it like this? Because I made my fraction only so big. What you said is good, though, of course. Okay, and then Nick, keep going. What about the derivative of 2 sine x? We good? Oh, somebody said it. Oh, sorry. I heard somebody say it. Nick, I thought it was you. I was looking down. They said it right. So Nick plus whoever else said it. Was that Ben? Oh, Mr. Flabbermouth over there. He's right. Sorry, Nick. I didn't realize it wasn't you talking. Does that make sense? Okay. All right. So that would be our derivative for that particular function. Any questions? Just got a couple minutes left here. Go ahead, Colin.
Differentiating any different than just finding the derivative.
That's the same thing. So differentiating is the act of finding the derivative. So like you can think of differentiating as like the verb form of derivative. It's actually finding it is differentiating. So that's in lieu of deriving, right? So deriving is not really the appropriate word to go with that situation. Okay, so we will, we'll get as much of this accomplished as we can, but we won't rush. I think we're in pretty good shape right now. So let's talk about rates of change. Think about what we've done here. We've talked about the derivative is, you all said, hey, it's the slope of the tangent line. We've dealt with that, right? You said it's the slope at a point. We've dealt with that. We really haven't talked about this rates of change thing yet. So let's talk about that really quick. The derivative is the blank rate of change. Instantaneous, yeah. Or you could say the rate of change at one point in time. So it's the instantaneous, I'll just abbreviate that, rate of change. Let's remember from maybe a physics class or maybe a pre-calc class or something, what is average velocity? You could think of this as a formula or a description. It doesn't really matter. What do you think? Go ahead, Ben.
Delta V over delta T.
Sure, delta V over delta T. And in this case, V would stand for what?
Velocity.
Ooh, but wait a minute. How could delta V over delta T be velocity?
Or
That's acceleration. So it should be delta
D. Or
X. I'll say X. It could be Y if it was moving up and down instead of left and right. It's basically delta position divided by delta T. Does that make sense? Okay, so then how do we formalize this? What does delta X really mean?
change.
Change in X. There you go. X2 minus X1, yeah. And then delta T would be
Interruption.
that.
This is Mrs. Harper. If you are interested in being a shadow ambassador and learning more about the program, please come to the meeting tomorrow at 12:30 in the Valor Center upper lobby. See you then.
Hey guys, let's finish this up. Let's at least do this first little part of this example. So it says if a billiard ball is dropped from a height of 100 feet, its height s at time t is given by the position function right there. If you've had physics, some of you, yes? Does that look familiar?
Yeah.
Kinematics, right? So believe it or not, we'll talk about where those came from this year. It's not really that difficult to see where they came from. They did not come from the mind of Newton or somebody like that. They came from calculus. And it's actually pretty easy to see where they came from. So there's your kinematic for position. S is measured in feet. T is measured in seconds. A just says find the average velocity over the time interval 0 to 2. So let's at least formalize this, and we can maybe pick it back up next time. So if I were to say average velocity, the symbol for that is this. V with a little bar over it. That means average velocity equals, let's see if we can put this into words. Let's use the formula you all said, x2 minus x1 over t2 minus t1. What would you think the x2 would be represented as?
0.
Oh, I don't know what the number is. Well, I guess I do now, but it's not 0. That would be the second position, or in this case, wouldn't it be the position when t is 2? So couldn't I just write it like this? S of 2 minus what? S of 0, all divided by 2 minus 0. I think we can finish this out. What's S of 2?
16.
64.
I think it's 36, right? Negative 64 plus 100.
Oh, shoot. I said, yeah.
So it'd be 36.
That's it.
What's S of 0? 100. So 2 minus 0, of course, is 2. What is 36 minus 100? Negative 64, of course, divided by 2 then is negative 32. And then what units would go with that negative 32? It's not meters per second. Be really careful with that. It is feet. So feet per second. That would be the average velocity. I want to leave you with this thought. When somebody dropped the billiard ball, the instant they released it, how fast was it going? Not going fast, though. It was going 0, wasn't it? The instant they dropped it. Please listen. Right before it impacts the ground, it was certainly not going 0. Right before it impacts the ground, do you think it was going faster or slower than negative 32? Doesn't it have to be going faster? If it started at 0 and averaged negative 32, wouldn't it have to be going a lot faster than negative 32 right before it hits the ground? And so next time we'll talk about how we could calculate the velocity at any point along the path as opposed to the average velocity over the whole path. Okay? Which is the derivative. Yes. Have a great day. See you guys.